Okay, so welcome to this video. In this video, what we're going to discuss is type 1 phosphoinositide 3-Kinase enzymes. Okay, and for short, phosphoinositide 3-Kinase enzymes are often abbreviated to PI3-kinase enzymes, or even shorter, just to PI3K enzymes. Okay, so phosphoinositide 3-Kinase enzymes, and as I say, these are usually just abbreviated to PI3-kinase enzymes. So phosphoinositide is usually abbreviated to P for phospho and I for inositide, or just to take it even further, it's usually written PI3 and then the kinase is abbreviated to K. Okay, right. So, the structure then for this video, we're going to start off by discussing what a phosphoinositide is. And in order to understand what a phosphoinositide is, we need to understand what phosphatidyl inositol is. Okay, so to understand then what phosphatidyl inositol is, we need to look at phosphoglycerolipids, and to understand what a phosphoglycerolipid is, we need to understand what a phospholipid is, and then we're going right back to what a lipid is. So we'll start with what a lipid is, then we'll talk about what a phospholipid is, then we'll progress up to phosphoglycerolipids, specifically looking at phosphatidyl inositol, and then we'll progress up to what a phosphoinositide is. Okay, we'll then talk about all of the phosphoinositide 3-Kinase enzymes, or the PI3-kinase enzymes. Okay, and then we'll focus in on type 1 PI3-kinase enzymes. We'll look at the 4 different types of type 1 PI3-kinase enzymes, and that will then focus in on the type 1A PI3-kinase enzymes, and specifically look at their structure in detail. Okay, and then we'll look at how they are going to be activated by receptor tyrosine kinases. Okay, right, so that's the structure for this video then. So, we firstly want to tackle this big word here. What is a phosphoinositide? Okay, so to discuss that, we're going to start off with what a lipid molecule is. Okay, so a lipid molecule is the fancy medical term for a fat molecule. Okay, now, what characteristic does a molecular structure have to have in order to be considered a fat molecule? Well, it needs to have an extremely neutral structure. Okay, this is the characteristic feature that all fat molecules have. They have an extremely neutral structure. Okay, and this means that they do not interact well with water. Okay, so a word we often use to describe fat molecules is hydrophobic. Okay, and the reason they do not interact very well with water is because they are neutral, and water is extremely polar. So let me remind you what this means. Okay, so let's draw a water molecule here. So a water molecule consists of an oxygen atom bound by single bonds to 2 hydrogen atoms. Okay, and in each of these single covalent bonds that we have here, there will be 2 electrons, one from the hydrogen atom and one from the oxygen atom. Okay, like so. Now, the question then is, do the electrons in these single covalent bonds sit right in the middle between the oxygen and the hydrogen atom, or do they instead sit to one side? Okay, and the answer is that they're going to sit towards the oxygen atom. Now, why is the question? Well, the electrons in this single covalent bond here, okay, and remember, one's from the hydrogen, which we'll have in red, and one's in from the oxygen, and we'll have that in blue. Okay, these electrons are going to be negatively charged. Okay, so they are going to feel attraction to things which are positively charged. Now, the nuclei of the oxygen atom and the hydrogen atoms are positively charged, because remember, nuclei contain a mixture of neutrons and protons. Neutrons are neutral structures, protons are positively charged. So that overall means that the net charge on the nucleus is positive. So the oxygen nucleus will have a positive charge, the hydrogen nucleus will have a positive charge. So these electrons here are going to feel attraction towards the nucleus of the oxygen and the nucleus of the hydrogen. Now the question is, which of these attractions is greater? Okay, well you might think, well surely it's going to be the oxygen because the oxygen has more protons in the nucleus than the hydrogen. The hydrogen atom only has a single proton, whereas oxygen will have far more than that. Okay, but you also have to take into account the fact that the oxygen nucleus will be shielded from these electrons by other electrons which surround the nucleus. Okay, so you can't just look at how many protons you've got, you've also got to look at the shielding of the nucleus by negatively charged electrons which are orbiting it. Okay, so there is a fancy word that people use which is the electronegativity of an atom, which basically means how good an atom is at pulling the electrons within a covalent bond like this towards it. Okay, and oxygen atoms, okay, here in blue, have a greater electronegativity than hydrogen atoms here in red. Okay, so that just means that the ability of oxygen atoms to pull electrons towards them is greater than the ability of hydrogen atoms to pull electrons towards them, which means that these electrons in this covalent bond here are going to sit towards the oxygen compared to the hydrogen. Okay, so they're going to be tilted towards the oxygen, and that's going to be the case for both of these covalent bonds. Okay, that will give the oxygen a partial negative charge here. Okay, so it's going to become partly negatively charged. And then it's also going to mean that these hydrogen atoms down here, those will become partially positively charged. Okay, because those have had those electrons taken away from them, so the positive charge of the proton is now no longer countered by the negative charge of the electron that it had here. Okay, so that results in these partial positive charges here. So that's what we mean by saying that water has an extremely polar structure. We mean that one side of the water molecule is positively charged and another side is negatively charged. Okay, right, so that makes it have two poles effectively. It's got two electrical poles. It's an electrical dipole, if you like. It's got a negative portion up here and a positive portion down here. Okay, right. Now this actually means that water molecules can interact with each other extremely well, because if I draw another water molecule here, okay, so here's another water molecule consisting of an oxygen atom with two hydrogen atoms bound to it. Okay, this oxygen atom will once again be partially negatively charged. Okay, so there's going to be a partial negative charge here, and these hydrogen atoms will be partially positively charged. Okay, so this partially positively charged hydrogen of this first water molecule is going to interact well with the partially negatively charged oxygen of this second water molecule. In addition, you have to factor in further the fact that this oxygen atom here is going to have two lone pairs of electrons sitting here as well, so it doesn't just have two covalent bonds coming off it, it also has these lone pairs of electrons. Now, a lone pair of electrons like this is a center of negative charge. This is a little center with a very strong negative charge there. Okay, so not only is the hydrogen going to interact with the oxygen because overall the oxygen atom has this negative charge surrounding it, it's also specifically going to interact with that center of negative charge, which is the lone pair of electrons here. So this is a lone pair. Okay, and that interaction it forms there between the hydrogen of one water molecule and the oxygen of the second water molecule here is known as a hydrogen bond. Okay, and for an intermolecular bond, which this is because it's not a bond within a molecule, it's a bond between two molecules, and therefore it's an intermolecular bond, meaning between two molecules. Okay, for an intermolecular bond, this is an extremely strong intermolecular bond. Okay, so this is good. Water molecules like interacting with other water molecules because they can form these strong hydrogen bonds here. Okay, right. So, if you put loads of water molecules together, they interact in this very strong way. Now, try and stuff a really neutral molecule into a mixture of water molecules. Okay, so let me give you an example of a really neutral molecule, which will be our first sort of archetypal example of a fat molecule. So there is a large category of fat or lipid molecules which are known as fatty acid molecules. Okay, these are also called long-chain carboxylic acids. Okay, so fatty acids is the old sort of colloquial biochemist name for them. Okay, the official sort of chemist name is long-chain carboxylic acids. Okay, right. Let me give you an example of a long-chain carboxylic acid. So all of these molecules are what you would consider lipid molecules. And basically this name, long-chain carboxylic acid, gives you a good amount of insight into what the structure of these are going to be. They're going to be a carboxylic acid, okay, so they need to have a carboxylic acid group, and they're going to have an extremely long hydrophobic tail, okay, and what makes it hydrophobic is that it's going to be extremely neutral. Okay, so let me give you the sort of prototypical example of a long-chain carboxylic acid. So the prototypical example is stearic acid, okay, and again, stearic acid is the old name for a molecule that would now be called octadecanoic acid. Okay, and although octadecanoic acid is a bit more of a mouthful than stearic acid, it's a useful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with an 18-carbon, fully saturated carboxylic acid. Okay, so let's draw this now. So here's our first carbon. Now we need to take the number of carbons up to 18, so we need to add on another 17. That means that 16 of them are going to be in the form of methylene groups within the middle. Okay, so here is a methylene group, and we're going to need 16 of these things here. Okay, so because I don't want to have to draw 16 methylene groups out, what I'm going to do is draw one methylene group here, put brackets around it like so, and then subscript it 16. And what this means is repeat this 16 times, basically. Okay, so that will take us up now to 17 carbons. We've got the first here, add on 16 to that, we'll go up to 17, and then we'll have the 18th over here, which will then have 3 hydrogens coming off it like so. Okay, so this is stearic acid or octadecanoic acid. Okay, now, this tail is extremely neutral, okay, because look at what it consists of. It consists of bonds between carbon atoms and bonds between carbon atoms and hydrogen atoms. If you have a bond between 2 carbon atoms, like so, the electrons in that bond are going to be nicely in between the 2 carbon atoms, because the electronegativities of these 2 carbon atoms are going to be the same, okay, so each of them is going to pull on these electrons equally, so the electrons will end up sitting in the middle, which means that this bond isn't going to be polar at all. It's not going to produce partial charges at all. Okay, then if we look at bonds between carbon and hydrogen atoms, again, carbon and hydrogen have roughly the same electronegativity. Okay, so these electrons are going to be sitting roughly in between the carbon and the hydrogen atoms. Okay, so again, these bonds are not going to be polar, so these are non-polar bonds, which means that overall, all of these atoms are just neutral. Okay, so if you shove a load of these molecules into a thing of water, okay, so loads and loads of water molecules, and you try and get them to mix, okay, so you shake it around, what will happen is you will get it to mix temporarily, but then it will unmix, it will separate into 2 layers, and the reason is that water molecules do not like interacting with these these neutral molecules here, such as stearic acid, okay, but it's not really a case of that they don't like interacting with this. They can form intermolecular bonds with this, but the intermolecular bonds they will form are incredibly weak compared to the hydrogen bonds. Okay, so water would much rather interact with other water molecules. It's far more energetically favorable to interact with other water molecules. So what happens is the 2 layers separate. Okay, so if we've got a container here, what will happen is the two layers will separate, and the reason they separate is because you are trying to make this interface between the water and the fat molecules as small as is possible, basically. Okay, so that the contact between water molecules and fat molecules is as small as possible. Okay, so these unfavorable interactions are minimized as much as possible. So, what ends up happening is that the water molecules end up shoving all the fat molecules into one area, basically. But it's not that the fat molecules love to interact with each other. They can interact with each other horrendously weakly. Okay, it's because the water molecules want to interact with other water molecules, and they end up shoving all of the fat molecules aside so that they don't have to interact with them that much. Okay, and this ends up creating an aggregation of lipid molecules. But it's not that lipid molecules like to interact with other lipid molecules, it's that the water molecules are shoving them aside. In fact, the lipid molecules will interact far better with water molecules. It's just the water molecules can't be bothered to interact with these, they'd much rather interact with other water molecules. Okay, so that's a basic introduction to what a lipid molecule is and why we call them hydrophobic. But it's really that water doesn't really want to bind to them, it would much rather bind to other water molecules, okay, rather than them hating water. It's more that water hates them, basically. Okay, right, so that's what a lipid molecule is then. Now let's turn our attention to what a phospholipid is. Okay, and this is going to be very, very important because PI3 kinases are going to phosphorylate phospholipid molecules, okay? So to have a good understanding of this, we need to talk about all of this. Okay, so phospholipids then now. What is the definition of a phospholipid? Okay, so to be considered a phospholipid, you have to obey two criteria. Okay, so let me run you through what these two criteria are. So, criterion number one then, okay, is that you need to have a lipid component within you. Lipid, okay? So you need to have at least one long-chain carboxylic acid, which I'll just call a fatty acid. So to be a phospholipid, you need to have at least one fatty acid within your structure. Okay, so that's one of the criteria that you have to obey in order to be considered a phospholipid. And then number two now. The other criterion is that you have to have a phosphate group within your structure. Okay, so this is the phospho portion of phospholipid. So let me tell you about what a phosphate group is. Okay, so a phosphate group, let me draw one of these here. So it consists of a phosphorus atom, double bound to an oxygen, okay, and at the moment I'm drawing an inorganic phosphate, okay, so I'm drawing a free phosphate molecule within the cytoplasm, so it's not yet added onto something. A phosphate group refers to it once it's been added onto something, okay, so this is actually a molecule rather than a group which I'm drawing at the moment. So it consists of a phosphorus atom double bound to an oxygen atom with two alcohol groups coming off either side of the phosphorus atom, and then a single bond off the phosphorus atom to an oxygen atom, which has then acquired an electron via ionic means and therefore has a negative charge. Okay, so this then is the structure of a phosphate group in blue here, or rather an inorganic phosphate at the moment, but we're going to add this inorganic phosphate onto molecules to create a phosphate group. Okay, right, so those are the two criteria then that you have to obey in order to be a phospholipid. You need to have a fatty acid within your structure, also called a long-chain carboxylic acid, and you need to have a phosphate group within your structure. Okay, right, we're now going to go a little bit more specialised. We're gradually building up. We're now going to talk about what a phosphoglycerolipid is. Okay, now all phosphoglycerolipids are phospholipids. Okay, so phosphoglycerolipids is a class of phospholipids, basically. They're not the only type of phospholipids. There are loads of different molecules which obey this criterion, and there's another major class of phospholipids that are present within cells, known as the sphingomyelins, that are not phosphoglycerolipids. But we're going to focus on the phosphoglycerolipids, and it's fair to say that the main types of phospholipids that are within cells are phosphoglycerolipids. Okay, and most likely if you've got a picture of a phospholipid within your head, that picture will probably be denoting a phosphoglycerolipid. Okay, so the name kind of gives it away. Phospho, and then we've got lipid back here, so that tells us it's going to have these two structures in. Okay, a fatty acid and a phosphate group. Glycero tells us that it's going to have glycerol in as well. Okay, so we're going to start by talking about the molecule upon which all the other phosphoglycerolipids are built, basically. So they're all based on this first molecule. So there is a core phosphoglycerolipid, the most basic of all the phosphoglycerolipids, the one from which all the others are derived. Okay, and we're going to start by discussing this phosphoglycerolipid. Okay, and this is phosphatidic acid. Okay, so I'm going to draw you a little cartoon structure of phosphatidic acid. So, we'll start with glycerol. So I'm not going to draw the actual skeletal formula for this. I'm going to draw a cartoon for it. Okay, so this vertical line that I am now colouring in green, this is going to represent glycerol. Okay, and glycerol is the old name for a molecule that would now be called propane 1,2,3-triol. Okay, and although propane 1,2,3-triol is certainly more of a mouthful than glycerol, it's a useful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with a 3-carbon molecule, propane, okay, where we have alcohol groups coming off the first, the second, and the third carbons. Propane 1,2,3-triol, to overall give us a molecule that has 3 alcohol groups coming off it. Okay, right, so onto these alcohol groups we are going to attach other molecules. Okay, so onto the alcohol group that comes off the first and the second carbon, we are going to attach long-chain carboxylic acid molecules. And I will show this like so. This is a long-chain carboxylic acid attached to the alcohol group that comes off the first carbon. This is a long-chain carboxylic acid attached to the alcohol group that comes off the second carbon here. Okay, so these horizontal lines that I'm now colouring in orange, these represent long-chain carboxylic acids, which I'll abbreviate to Fa for fatty acid. Okay, right, so we are going to attach these long-chain carboxylic acids onto the alcohol groups that come off the first and the second carbons of the glycerol molecule via ester links. So let me just remind you of what an ester link is. So here is a carboxylic acid group, okay? Here is the R group of the long-chain carboxylic acid. So R here just means an arbitrary group, effectively. Okay, so you've got some arbitrary group here. Okay, then we've got the alcohol group of the glycerol molecule. So let's colour this in. The glycerol molecule will represent in green. Then we'll represent this arbitrary group of the long-chain carboxylic acid in orange here. Okay, right, so to form an ester link, what you're going to do is you're going to take the alcohol group off the carboxylic acid group of the long-chain carboxylic acid. You're going to take the hydrogen off the alcohol group of the glycerol molecule. You're then going to attach the carbon of the carboxylic acid group to the oxygen of the alcohol group, and this link that you create here, this is known as an ester link. Okay, and the reaction which produces this ester link is also going to produce water and is therefore called a condensation reaction. Okay, right, so that is how we are attaching these long-chain carboxylic acids onto the alcohol groups that come off the first and the second carbons of the glycerol molecule. Okay, now that's not yet phosphatidic acid. That would just be a diacyl glycerol molecule. Okay, to turn it into phosphatidic acid, we are going to attach something off this, the alcohol group that comes off the third carbon of the glycerol molecule. Okay, and we are going to have to attach a phosphate group. I mean, we're not even going to get to be a phospholipid unless we attach on a phosphate group. Okay, so here we are going to attach on a phosphate group. So let me talk about the addition of this phosphate group onto the alcohol group of the glycerol molecule. Okay, so let me draw an inorganic phosphate at the moment. So here is a phosphorus atom double bound to an oxygen with two alcohol groups coming off it, and then a single bond to an oxygen atom, which has then acquired an electron via ionic means and therefore has a negative charge. So this is our inorganic phosphate group. Okay, then here is the alcohol group that comes off the third carbon of the glycerol molecule. Okay, so how do we attach on this phosphate group onto the alcohol group of the third carbon of the glycerol molecule? Well, actually, it's extremely similar to the esterification reaction up here, because if we look at this group that I am circling in pink here, this contains a phosphorus atom double bound to an oxygen atom with then an alcohol group coming off it. Okay, now that looks extremely similar to a carboxylic acid group up here. In fact, if I replace that phosphorus atom with a carbon atom there, that would be a carboxylic acid group. Okay, so this is actually going to react with this alcohol group in much the same way as the carboxylic acid group interacts with an alcohol group. Okay, so what's going to happen is the alcohol group is going to come off the phosphate molecule. The hydrogen is going to come off the alcohol group of the glycerol molecule, and then we're going to attach the oxygen of the alcohol group to the phosphorus atom of the inorganic phosphate molecule here. Okay, and this is now known as a phosphoester link, to draw the parallels that exist between it and an ester link. Okay, so that's how we're going to attach this inorganic phosphate molecule onto the alcohol group that comes off the third carbon of the glycerol molecule, and now this is a phosphate group because it's stuck onto a bigger molecule. Okay, so remember, a molecule is an entity in itself. A group just means part of a molecule, basically. Okay, right, so this is phosphatidic acid, okay, and firstly, it's the core phosphoglycerolipid. All the others are going to contain this molecule. They're just going to be bigger, basically. They're going to have extra groups stuck on the side of them. Okay, now let's firstly just check that it satisfies the conditions of a phospholipid. Okay, so remember, the two criteria for being a phospholipid were that you needed to have a fatty acid within your structure. Well, that's certainly true. We've got two of the things in our structure here. Okay, so that's fine. And you need to have a phosphate group within your structure. That is also fine. Okay, and in fact, this name makes complete sense because we've got a phosphate group, we've got our lipid components, and then we've got glycerol in, and that's all we've got, basically. Okay, and this is the molecule that's going to be core, foundational to the formation of all of these molecules. So this is the starting point for forming the rest of these. We'll come to how we generalize it in a moment. Okay, right, so the first thing I want to say is that there is not just one phosphatidic acid molecule, okay, and that's because I did not actually specify what long-chain carboxylic acids you were meant to put in these two positions here, okay. They could have been anything, basically, and they don't even have to be the same one. You can have one type of long-chain carboxylic acid here and a different long-chain carboxylic acid here, okay. So that means that this is actually a whole family of different molecules which would all have different long-chain carboxylic acids here. However, for the properties of these phosphoglycerolipids, it's not going to make a huge amount of difference what long-chain carboxylic acids you put there, as long as they're all very neutral. Okay, right. The second thing I want to say is what the difference between phosphatidic acid and phosphatidate is. Okay, so people hardly ever talk about phosphatidic acid. They always talk about phosphatidate, and I want to tell you what is the actual difference between phosphatidic acid and phosphatidate. Okay, so Phosphatidate is what would be called the conjugate base of phosphatidic acid. Okay, now what does that mean? Well, let's firstly discuss why phosphatidic acid is actually an acid, and then we'll come to what the conjugate base of an acid is, and then we'll arrive at, therefore, at what phosphatidate is. So, basically, the reason that phosphatidic acid is an acid is that it contains this group that I am now circling in turquoise. So even once you have formed this phosphoester link that we've got here, okay, this group that I'm now circling in turquoise, this is still intact. Okay, it consists of a phosphorus atom double bound to an oxygen atom with an alcohol group coming off. Okay, so that group there is still intact. And remember, this group is another one of these groups that is analogous to a carboxylic acid group. In fact, again, if we replace that phosphorus atom there with a carbon atom, that would be a carboxylic acid group. Carboxylic acid groups can donate that hydrogen atom's nucleus to the solution, okay? And so can this carboxylic acid-like group that we have now within our phosphatidic acid molecule. So basically, what can happen is if we look at this alcohol group that you have within that turquoise outlined group here, this is going to contain a single bond where the hydrogen has added an electron and the oxygen has also added an electron. Now what can happen is this hydrogen nucleus here can go off without the electron. It can leave its electron behind. Okay, so remember, hydrogen atoms only have one electron. Okay, usually hydrogen atoms just consist of a proton at the center. Okay, so we'll colour that in blue. And then an electron orbiting around. That's the most common isotope of hydrogen. There are other isotopes of hydrogen where you have a different number of neutrons in the centre. Okay, so protium is the main form of hydrogen that's all around us. Okay, and this just consists of a proton at the nucleus with an electron orbiting around it. There are then other isotopes of hydrogen, for instance deuterium, which contains a single neutron in the nucleus as well, and then finally the other one that I know the name of is tritium, which has two neutrons in the centre basically, and presumably it can go on, but I don't know what the names after that are. Okay, right. However, the main isotope of hydrogen is protium. So usually the nucleus of a hydrogen atom will just consist of a proton. Okay, so once it leaves its electron behind, it will be donating this proton into solution. Okay, now that's the definition of an acid. An acid is a molecule that is capable of donating a proton into solution. Like this molecule could potentially lose that proton off this alcohol group here and donate it into solution. Therefore, it is capable of donating a proton into solution and is an acid. Okay, now, what's the concept of a conjugate base of an acid molecule then? Well, let's illustrate this in the case of the example of phosphatidic acid. What happens once the phosphatidic acid molecule has actually donated its proton away into solution? Okay, so once it's donated its proton away into solution, this oxygen atom here will be left with an additional electron and therefore will have a negative charge. Okay, and now no longer does it have that hydrogen atom here anymore. Okay, it's kept the electron, but the proton has gone. Now, the question is this remainder molecule, is this an acid anymore? Okay, well, what was the definition of an acid molecule? It was a molecule that was capable of donating a proton away into solution. This molecule that we've got left is not capable of donating a proton anymore away into solution. It's got a negative charge on this oxygen and another negative charge on this oxygen. It doesn't have any more protons ready to donate. So it's not an acid anymore. Okay, it is in fact actually now a base. Okay, because it can actually receive protons from solution. So remember, a base is a molecule which is capable of receiving protons from solution, the exact opposite of an acid. Okay, so what can happen is a proton can come from solution and bind to that negative charge on the oxygen. Okay, so this molecule is actually capable of taking protons out of solution and is therefore a base. Now, because we got this molecule by removing the proton from an acid, it's called the conjugate base of the acid. So this is what phosphatidate is. It is phosphatidic acid once phosphatidic acid has lost its proton and therefore has a negative charge on that oxygen. Okay, so that is what phosphatidate is. Right, so the reason that people talk a lot about phosphatidate and then never talk about phosphatidic acid is that you do have some of these molecules within the cell membrane. Okay, now under physiological pH, which is around 7.45, most of these molecules have lost their proton and therefore exist in the phosphatidate form rather than in the phosphatidic acid form. So most will exist in this form, a tiny fraction will exist in this form, which is why everyone talks loads about phosphatidate and then hardly anything about phosphatidic acid. Okay, right, so that's phosphatidic acid. Let's us now discuss how we are going to generalize phosphatidic acid to create a more general phosphoglycerolipid. Okay, so it all comes back again to this group that I have circled in turquoise here. Okay, so remember, this is this carboxylic acid-like group here. Okay, and we know that these things can interact with alcohol molecules on other alcohol groups on other molecules. Okay, so if we were to bring in some other molecule which has an alcohol group on it, then what can happen is this carboxylic acid-like group here can form a phosphoester link with this alcohol group containing molecule. So what can happen is the alcohol group can come off this alcohol group, not like that, cross that out, it's the other way around. The alcohol group can come off the phosphate group, the hydrogen can come off the alcohol group. Okay, those two things can form water, and then this phosphorus atom will bind to the oxygen atom of the alcohol group on this other molecule, again via a phosphoester link. So basically the phosphate group can bind onto the glycerol on one side, and then onto this other molecule which has an alcohol group on the other side. Okay, via these two phosphoester links that we have here. Okay, so that's how we are going to create more general phosphoglycerolipids, by binding molecules which contain alcohol groups onto the carboxylic acid-like group of the phosphate group of the phosphatidic acid molecule. So putting on this alcohol group containing molecule here creates us a more general phosphoglycerolipid. Okay, so you will notice that they all contain phosphatidic acid. It is the core structure of all of the phosphoglycerolipids. Okay, right, so what we'll discuss in the next video is an example of one of these phosphoglycerolipids, namely phosphatidyl inositol, which is where we have attached on an inositol molecule onto the phosphatidic acid molecule.